previously, we've looked at the process of diagonalizing a matrix, right? And we realized that it came down to finding the eigenpairs, right? And but then it kind of raises a bigger question. When is that process possible, right? And if it's not possible, what is hindering that process? So now we're going to take just a little bit, take a brief look at a little bit of the theory that tells us when diagonalization is guaranteed. And the first thing that we're going to start with is a theorem, and we're going to actually prove this theorem. And the theorem states this, that an n by n matrix is diagonalizable, right? So is diagonalizable if and only if it has n linearly independent eigenvectors. Right? So that's what it comes down to. So it's not surprising that this necessary and sufficient condition comes down to having a certain number of independent eigenvectors. All right, so let's take a look at the proof of this. Now, because it's an if and only if proof, we have to prove both directions. So let's start by assuming that the matrix is diagonalizable, right? So suppose A is diagonalizable. Right, well, what does that mean? Well, we know that there exists some diagonal matrix such that P inverse times A times P, right, where P is invertible, which we could also write as saying that A is P times D times P inverse. And if I wanted to, I could actually say that A times P is equal to P times D. So remember, all of these are equivalent, right? With the understanding that D is diagonal and P is invertible. Clearly, we're making reference to the inverse of P, so it better be invertible. All right. So we have this P, so let's denote P kind of in matrix form, but I'm just going to identify its a column. So I'm just going to say here's going to be P1, that's going to be a vector, and then this will be P2, and then of course this will go up to Pn, right? So this is just the matrix P. It has to be an n by n matrix. And so it's going to have n columns, and I'm just saying that here are the columns identified as these column vectors, right? And then we know that D is a diagonal matrix, right? So since D is a diagonal matrix, then I know I can write it, well, at least a couple ways. I can say that it is diagonal. Now, I don't know what the numbers are on the main diagonal, but there's some real numbers. So I'm just going to say it's lambda 1, lambda 2, dot, 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 lambda n, where our lambda I, again, is just some real number. And we're using, we're working with the field of real numbers, but you can certainly do this with complex numbers, right? Nothing breaks, all right? So then let's write down these two expressions, right? So let's write down the A times P. Right, so A times P. So that's basically, so remember when you're doing your like row times columns, and you're going to do all the rows of A times the column P, then again we're going to get another matrix, and it's basically going to be A times P1. And then do the same thing, take all the rows of A and multiply the second column. So you'll have A times P2, and then dot, 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 A times Pn, right? So this is really just kind of the symbolic way of representing what we do when we multiply two matrices, right? So there's that. And then let's write down the P times D. Now, because D is diagonal, and this is the key, remember when we were multiplying by a diagonal matrix, what you end up doing is just multiplying the corresponding row by the corresponding scalar, right? So what would happen is all the rows in column 1 would get multiplied by lambda 1. So you'd have lambda 1, and then you'll have your P1. And then same thing, all the rows in column 2 will get multiplied by lambda 2. So you'll have lambda 2, and then you'll have your P2, and then dot, dot, dot. Then you'll have your lambda n multiplied by Pn. Right? So we have this. So we have our two matrices. Now, here's the key. We're saying that these two matrices are equal. So what that means is this column has to be equal to that column. And this column has to be equal to that column. And then this column has to be equal to that column. So basically, I'm just going to write it down. So therefore, our A times Pi is equal to lambda I times Pi. But this is basically the equation for an eigenvalue and an eigenvector. So this implies that lambda I and Pi is an eigenpair, so is an eigenpair of A. Not only that, but because P is invertible, right, so here's the key. So since P is invertible, remember we have all these equivalencies or sufficient things that relate to invertible matrices. We know that the columns of P are linearly independent. So this implies that our Pi's, or actually let me write it like this. So P1, I don't know why I started doing hats, and then Pn are linearly independent. Right? So that proves the first part of the statement, that if the matrix can be diagonalized, right, then it has to have n linearly independent eigenvectors, right? So we got the eigenvectors from this equation, and then we got the linearly independent from invertibility. Well, what about the other way? So suppose, right? So let's do this. So suppose A has n linearly independent eigenvectors, right? So that's the other direction now. Now we have to show that we can sort of do the diagonalization process. Well, so this means, so I'm just going to say, I'm going to use the same notation I did above. So if we have our eigenvectors, then they always have to come with an eigenvalue, right? Remember, they're pairs. So let's just say that lambda I and Pi, right, are eigenpairs of A, and in this case, yeah, I goes from 1 to n, right, n of them, because they're n linearly independent eigenvectors. And then here's what we're going to do. We're going to basically mimic what we did in the previous video in sort of constructing the D and the P. So we would let P be equal to the P1, and actually I don't need a comma there, I'll just space it out, and then P2, and then dot 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 Pn, right? And let's let our D be, again, the same thing that we have, the diagonal matrix, and then lambda 1, lambda 2, dot, 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 lambda n. And then if we go through and write down those two products again, so if we do A times P, right, we know what that's going to look like. It's going to be, so we got our A times our P1, P2, Pn. And what does that give us? Well, it would be A times P1, A times P2, dot, 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 A times Pn. And again, by, so then this would be equal to, now if we do the P times D, actually, let me erase this last equal sign here. And then if we do the P times D, so with, again, multiplying by a diagonal matrix, we will end up getting so P times D, we will have our P1, P2, dot, 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 Pn, and then times the diagonal matrix, lambda 1, lambda 2, dot, 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 lambda n. And again, we know what will happen is that these scalars will multiply the corresponding columns. So we end up having the lambda times our P1, lambda 1 times P1, lambda 2 times P2, dot, 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 lambda n times Pn. And since these are eigenpairs, we know that these two are equal. So again, what we have kind of matched up is this is going to be equal to this. And then this is equal to this. And then finally, this is equal to this. So what does that mean? It means that A times P is equal to P times D, and then therefore we can write this either way we'd like. So we can say that A is equal to P times D times P inverse. So therefore A is diagonalizable. Right? And then that's our QED. All right. So that just kind of shows you that the necessary and sufficient condition for a square matrix to be diagonalizable is that it has n linearly independent eigenvectors. Now, what could guarantee having n linearly independent eigenvectors? One thing that is sufficient but isn't necessary is the fact that you have n distinct eigenvalues. So I'm going to state that theorem, but I'm going to state that theorem without proof, right? Just so that we can keep the video a little bit shorter. So it says this. So if A is n by n and has n distinct, so no repeated, right? So n distinct eigenvalues, then A is guaranteed to have n linearly independent eigenvectors. right? So if you find the roots of the characteristic polynomial and you get n distinct roots, right, then the matrix can be diagonalized, all right? So when can this fail? So let's take a look at a simple 2 by 2 example. So let's say we have a matrix A that's of the form 2, 1, 0, 2. Right? Now notice, this is upper triangular, right? So this is upper triangular. And then we know about triangular matrices is that it's fairly easy to identify their eigenvalues. It's just the entries on the main diagonal. But in this case, our lambda 1 and lambda 2 are equal to 2. So what we would actually say is that lambda equals 2 is a root of p of lambda with what's called an algebraic multiplicity, right? So an algebraic multiplicity of 2. It's a double root. Let's see what the eigenvector would be when we try to find the eigenvector for this. So then let's look at our A minus 2I times V. So we're going to set up this homogeneous system. So we're going to end up subtracting 2 from the entries on the main diagonal, and look at what we end up getting. 0, 1, 0, 0. And then there is our homogeneous system. So in this case, our x1 would be a free variable, and then x2 would have to be equal to 0. So the eigenvector here is of the form t0, and then a basis for these eigenvectors would just be 1, 0. And there's no other eigenvector, right? So in this case, the eigenspace that corresponds to this eigenvector is one-dimensional because there's only one vector in the basis. So the eigenspace, right, corresponding to lambda equals 2 is one-dimensional. I can only find one linearly independent eigenvector that spans that space, right? And this is what we describe as the geometric multiplicity of the eigenvector, right? So in this case, the geometric multiplicity of V1 is 1. Right? So therein lies the problem. We have an algebraic multiplicity of 2, so we have a double root, but we basically just have a single eigenvector. So we have a, and this is problematic. So this matrix A is not diagonalizable. So A is not diagonalizable. Right? So there are some matrices out there, right, where this, as much as we would like to be able to do this, it's not possible. So I'm just going to summarize. I'm not going to write this down, but I'm just going to say a couple things. For a matrix to be diagonalizable, there has to be n linearly independent eigenvectors, right? And one way to ensure that is that you have n distinct eigenvalues, right? Then your matrix is diagonalizable. But it is possible that repeated eigenvalues might still work, but you'd have to check the eigenspaces to see, okay, what is the dimension of the eigenspace, right? But unfortunately, some of those matrices, and sometimes they're described as being deficient matrices, they don't have the required geometric multiplicity. And another interesting thing too is, going back to another key concept in linear algebra and vector spaces, is that when you have n linearly independent vectors in a vector space, then you have a basis. So we can actually say this: a matrix is diagonalizable if and only if its columns, or I'm sorry, its eigenvectors form a basis for that dimensional space, right? So again, there's so many connections that are rampant in linear algebra, and eigenvectors and eigenvalues is just one more dimension to that, I should say. All right, so there you go. That's just a little explanation as to how this process works, and unfortunately sometimes when it fails, right? Hope to see you in the next video.